So we have been talking about similarity in shapes yesterday. That's what we talked about yesterday. What was similarity? What caused two shapes to have some, or what were some things that happened with similar shapes? So what did we notice yesterday? What was sort of our definition of similarity? When we had two shapes that were similar to each other, what did we find was true with those two shapes? They have the same angles, good. So similar shapes always have the same angles. And there's one other thing. I'm going to use our fancy word proportional. They have proportional side lengths. So anytime you have two shapes that are similar, you can assume, always, you'll know, that all of those angles are going to be the same, and that all of those side lengths will be proportional. And it is always proportional based off of that scale factor, whatever that scale factor was. So, looking at these two triangles, how can we go about solving for a scale factor? How can we go about finding a scale factor of these triangles?
You have to do like your RM or something.
So we won't worry about solving for RS at the moment.
Okay.
We just want to figure out what was the scale factor, because if we think about dilation, it always was a scale factor that was able to grow the shape or shrink the shape. And our dilation was one way that we got similar shapes. And so what was that scale factor that we multiplied each of these sides by to shrink our shape down from ABC to XYZ? So in order to do that, we'll have to find two sets of corresponding, or we'll have to find a set of corresponding sides. So do I see a set of corresponding sides on both these triangles that I have values of?
20 and 21.
So 20 is AB. AB matches to XY, which is R. So 20 and R match up. What's going to match up with 21? YZ and BC. So 21 and 28 will be corresponding sides. And so because 21 and 28 are corresponding, we can use that to create our ratio, our fraction, or to figure out what our scale factor is. Once again, we like to put our second triangle in our similarity. So in this case, XYZ is going to be the numerator of your scale factor. So I'm going to put 21 in my numerator. I'm going to put 28 in my denominator. And this is my scale factor I'm going to use. So 21 over 28 can be considered a scale factor, but typically we like to simplify that fraction. We want to get it in the most simplest forms. So can we reduce this fraction? Can we simplify it to find a better number for our scale factor?
Yes.
What can we simplify it to?
3.
3 over 4. These are both divisible by 7. So 21 divided by 7 is 3. 28 divided by 7 is 4. So we can reduce this fraction down to 3/4. So each of these each of these side lengths of our triangle are 3/4 of our size of our original triangle. We take 28 multiplied by 3/4 and we end up with 21. It's shrunk by 3/4. So that's our scale factor. The other thing we want to do on this warm-up is we want to find these missing variables. We want to find what is R and what is S. Let's start off with S, and let's start with those angles. How can we go about finding our missing angle S from this problem?
Seem like the same thing. Seem like put that one as like the same thing, and then you go your 180 minus 95.
So angle B is corresponding to angle Y. So we know corresponding angles are the same in similar triangles. So 28 is going to be what Y is. And now we have two of our angles in our triangle. So we know we can solve for them by doing 180, that interior angle sum of a triangle, minus our other two angles. And that gives our missing angle, which should be 57 degrees. Okay, let me see the nurse. So using those same angles from our similar triangles, we were able to solve for that missing variable. So we have one other variable we want to solve for. We want to solve for R, side R. So what side is going to be corresponding to R? AB. So AB is 20. So 20 and R are corresponding side lengths. Those are going to be proportional. So if our proportion that we had before was 21 over 28, we know proportional signs create equivalent fractions. So we can create an equivalent fraction of 21 over 28 with good. From here, we just need to cross multiply, and then we can solve. So 21 times 20, that gives us 420. 28 times R, 28R. Divide by 28. And this leaves us with R equals 15. So, by creating those proportional sides or using those same side lengths, we're able to solve for that missing piece of information. We're able to solve for those missing pieces. Or another way you could have solved for this is you could realize your scale factor is 3/4. If I start with 20, I can multiply it by 3/4, and that's going to give me my shrunken side length of 15. That's another way to solve it if you know the scale factor. If not, create a proportion with your sides and just use that information. So there's a couple ways you can solve for those missing angles.
So it does not ask me for the scale factor, you just go right into.
Yeah. We were just the main reason we had to do this one is because we had that scale factor part. But if it was just asking for finding the missing sides or finding the missing variables, you could jump right into finding for S or for R. We just had that also in our warm-up. Any questions about what we did yesterday? All right. So once again, similar shapes. It's not just triangles. We're going to focus in mainly on triangles today and what makes similar or what makes triangles similar specifically, like how we focus with congruent triangles. But similar shapes, these proportions, they can work for any shape: a square, rectangle, pentagon, a nonagon. It doesn't matter. You can get a similarity in any shapes, but this is specifically for triangles that we're going to talk about today. So I know we already mentioned this in the warm-up, but what were those two things that were required with similar shapes? Same angles and proportional sides. Angles, proportion.
What is proportional?
So, proportional, that was our word for if you were creating equal fractions. So if I figured out what this side length was, let's say these side lengths are corresponding, I'm going to use X. So corresponding side lengths, if we create fractions of corresponding side lengths, they should be equal to each other. So X divided by 8, that's a fraction with my two corresponding side lengths. These should be proportional or equal to Y divided by B, another set of corresponding side lengths, which is also equal to my other set of side lengths, which is Z over C. So if you create fractions of those corresponding side lengths, they're all going to be equal to each other. So if we know 3 of those pieces of information, we can solve by cross-multiplying for that last piece. So that's what our proportional sides meant. So every shape had same angles and proportional sides as long as they were similar to each other. So that's a lot of things to show, though. In order to figure out two shapes are similar, you have to show all those sides are proportional. You have to show all of those angles are the same. That's a lot of information to go through. So just like what we did with congruence criteria, we're going to try to cut this down so we can find some shortcuts. Rather than having to show every side and every angle and all that information, let's see if we can cut it down to 2 or 3 things that we can show in order to show 2 triangles are congruent to each other. Or 2 triangles are similar to each other. So thinking back to our congruence criteria, what were our 5 criteria we used to prove 2 triangles were congruent? Side, side, side. What else?
Angle side.
Angle side. Angle, angle side. Angle side, angle. And hypotenuse left. So these were the 5 that worked. These were our 5 criteria that worked. We were able to short it down to, if we got one of these 3 situations, one of these 5 situations, we were able to prove that they were congruent without having to do everything. What were the 2 that didn't work? What were 2 shortcuts that? So side side angle or angle side side, that one did not work. Angle, angle, angle did not work either. So the reason side-side angle, the reason that one didn't work is if you had two side lengths and an angle, you were able to sort of swing that last side length to create two different triangles, one with a really long side length and one with a really short side length. We saw that a little bit on the computer thing that we were doing. Why didn't angle, angle, angle work? Why weren't we allowed to do angle, angle, angle? Why didn't that always give us congruent triangles?
Because you could put them anywhere.
I know, maybe if you make diagonally, say that you have the same angle.
So with angle, 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 it was possible to create two triangles, but you had to position those triangles all in the same exact location in order for them to be the exact same triangle. If you put those angles, that was a bad example. I'll show you that without changing it. If you put those angles in different locations, or if you stretch those angles out, we created that dilation of those angles. We had two triangles with all of those same three angles, but those side lengths are obviously not the same. So with angle, 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 we weren't able to create congruent triangles, but what can you guess about those two triangles? They're similar. So angle, angle, angle does not work for congruent triangles, but it does allow you to prove similar triangles. If you have two triangles that all have the three same angles, all your side lengths will always be proportional. And so you'll have your three proportional sides, you'll have your three angles, and so you will always create similar triangles as long as you can sort of show angle, angle, angle. And so that's one criteria we can use if we ever need to show triangles are congruent. Now, we won't have to sit down and do a two-column proof to prove two triangles are congruent to each other. That's not something we'll have to worry about. We will have to do some stuff to see if we can show two triangles are congruent, but it won't be like a formal two-column proof like what we did with the congruent triangles. But angle, angle, angle is one of the options. If we can show three angles are congruent, then we can show those triangles are automatically similar to each other, and then we can solve for those missing pieces of information, solve for those missing sides, things like that. What was that?
So what's up with stripes?
With stripes?
Yeah, you have stripes, you have stripes, one has stripes, and now there's like stripes.
That's kind of that's the stuff we want to color with it.
Thanks, Kate. Okay. That's just what I said. If we can show all three angles are congruent, it doesn't work for congruent triangles, but it does show us the triangles will always be similar to each other. It's possible for them to be congruent, but it's not always set in stone. So I have two triangles here. How can I show that these two triangles are similar to each other? What would I have to do?
Put in them. I'm missing angle.
We just talked about how if we can show all three angles are the same in these triangles, then we can show that they're congruent to each other. So if we can find these missing angles, we can show that they're hopefully similar. So 24 and 24 already have one match. How can I find this missing angle? 180 minus 24 minus 92. We go through that math, it should give us 64 degrees. Oh, 64 degrees. That's the same as 64 degrees down here. $64 plus 24 plus 92 has to equal 180. So that means this one has to be 92 as well. Well, wait a minute though. We were able to show that they were similar without having to show three of those angles were similar, or three of those angles were congruent. We just did two of them, and we were automatically able to assume that third one was correct, right? So do you think we can shorten angle, angle, angle? Because we showed two angles were congruent, and that automatically forced our third angle to be congruent. So that means rather than having to do angle, angle, or angle, 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 we can cut this down to just angle, angle similarity. If you can show two of those side lengths are congruent, or two of those, sorry, not two of those side lengths, two of those angles, if you can show two of those angle measures are congruent to each other, those third angle measures have to be congruent. There's no other way. If you put the same numbers into a formula every time, you're going to get that same answer every time. So if we put those same two angles in, solving 180 minus those same two angles, you're going to get that same answer no matter what. And so as long as we have two angles that are the same, we can always assume similar triangles. And that works for any two triangles. As long as you can show they have two of the same angles, they will always be similar to each other. Now once again, that means your sides are going to be proportional. So it's not the same as congruent, but it shows they're similar, which is nice. And this can be very helpful for solving for missing sides. As long as you can show you have two similar triangles, you can solve for a lot of missing pieces of information. And then this becomes important in the future when we talk about trigonometry. Because it's a big, nice theorem that we'll use in the future. Angle, similarity. Two congruent angles, always similar in triangles. So we're going to talk about one other main thing today. And this is called the triangle proportionality theorem. It's a big name, big words. What the triangle proportionality theorem says is if you have a triangle and there is a parallel line that is parallel to one side of your triangle, so you create a parallel line, and that parallel line cuts through two sides of your triangle, it will divide these proportionally. So if I were to create fractions, let's say this is a, b, and this is x, y, a over b is going to be proportional to x over y. So always create proportional pieces of your other two side lengths, but specifically of these two side lengths. These two will be proportional by that same ratio, but it's like the full thing to this one. And so that's very helpful with solving for missing pieces of information, because if you have this side length, but you're missing this little piece, rather than having to know the full side length of the triangle, you can solve for those missing pieces as long as you have those parallel lines. But that's not the only thing the triangle proportionality theorem does. It also automatically makes your triangles similar. So creating that parallel line in there automatically gives you two similar triangles. Now let's try to figure out why this works. We can assume it's true just by believing what everything Mr. Jarvis says. But based off stories I've told you in the past, you know that not everything I've told people is true. Santa is real. All right. So let's see if we can prove this. Figure out on our own. Let's see if we can prove this, that these are similar triangles. How can we show that my smaller triangle DEC is similar to my larger triangle ABC? So we know, based on our similarity theorems, if we show two angles are congruent, then we have similar triangles. So we just need to find two sets of similar angles, or congruent angles. So I have AB, or ABC, and DEC. What do they automatically already have together? C, they both have angle C. They are both included in that angle. So that's one set of angles that I know they both have. I need to just find one more. One more set of corresponding congruent angles to give me similar triangles.
You get like what's your parallel lines?
So I have parallel lines. So parallel lines gave us all those different angle pairs. Let's see if we can find one of those. Can I figure out what type of parallel angle pair I have with A and D? Corresponding. Good. So corresponding angles are always congruent. So we've shown that we have two sets of congruent angles. Therefore, our angles are or therefore our two triangles are always similar. So anytime you have a set of parallel lines, you will always create similar triangles. It doesn't matter where those parallel lines are, whether they're like right here, or whether they're all the way up at the front. It doesn't matter. You will always create two sets of similar triangles. And it will always divide these side lines proportionally. And this is a big theorem, and it's really helpful for solving for missing pieces of information or proving triangles are congruent. So let's look at some examples of this. So I have this triangle right here, ABC, and then I have this parallel line ED that gives me EDC. I am looking for the side length of JE. No, I'm sorry, AE. JE is the second one. I'm looking for this side length. Our triangle proportionality theorem tells us that these parallel lines divides my angle, or divides my side length proportionally. So these two sides are proportional, or the way they're divided up are proportional to my other two sides. So if I can create a fraction of these, I can set it equal to my fraction of AC. So I'm going to put BEC in my numerator. It doesn't matter which way you flip it, but we're typically used to putting our second triangle in our numerator, so I'm going to keep that strategy, keep that up. If you flip it around and put the other number in the numerator, you'll still get the same answer as long as you're consistent. But I like to put my second triangle in the numerator just to keep it consistent. So 75, or not 75, 7.5 over 2.5, that is an equivalent fraction to my 6 divided by my x. So I took my longer side divided by my shorter side. I set that proportionally equal to 6 divided by my shorter side. From here, we just have to cross multiply, and then we can solve. 7.5 times x, 2.5 times 6, gives us 7.5x, and then 2.5 times 6 is 15. From here, we just need to divide by 7.5, and we're done. X equals 2. Are we okay with this one? So see if you can do the same strategy. See if you can solve for the second one. See if you can find what those side lengths of JE is going to be using that same proportionality. Okay, what did we find for this side length? How are we able to go about finding this?
You have to put 12 over 4.
12 over 4.
And that equals 9 over x, or whatever that is. And then do your cross multiply. Into 12x equals 6.
Good. So we saw 12 over 4 was one of our proportional sides. So that made 9 over our variable x, or missing side length. So you can set up those as equivalent fractions. Cross multiply, we get 12x equals 36 divided by 12 gives you 3. Okay. And so that is how we can use that triangle proportionality theorem to help us solve for those missing side lengths. And once again, these will always be similar triangles. All those triangles are similar to each other because they automatically have those two angles that they share. So typically the newer triangle is in the numerator. So in our first case, our smaller triangle was this one, but in this one, our second triangle could go anywhere. It doesn't really matter. You get the same answer either way, but typically our second triangle, or like the new dilated triangle, is going to go right for the scale factor. But with these types of problems, you're going to get this right answer either way, as long as you're consistent and put the same triangle on the top as the same triangle. That doesn't really matter. So these parallel lines might look similar to something we talked about in the past. So in the past we talked about the mid-segment theorem, which said that if we have a midpoint of towards our sides, and we connect a line through it, we created a parallel line to the base that was always half the length of our base. And the reason this was true is because this triangle proportionality theorem. As you create that parallel line, it's going to cut those sides proportionally. So in this case, those proportions was always 1 to 1. So this side is going to be equal to that side. You're always creating those ratios of 1. And so this was always going to be half of your base because of it. So that was one, or triangle, or mid-segment theorem that we talked about in the past, and how it relates back to this stuff. There was a reason for that. Were you saying something? I thought someone was saying something.
I was, but then I realized.
Alright, so one last thing. So this is our last final problem. So in the diagram of ABC, we have line DE that's parallel to line BC. And we have AD equaling 3 units, DB equaling 2 units, and DE equaling 6 units. We want to find the length of BC in this problem. That's our length that we're looking for. So we have a parallel line. So we know this is going to divide our sides proportionally. But the thing is, those proportionalities only work for those two sides. So in this, we're going to have to look at similar triangles. We have two similar triangles here. We have our original triangle, ABC. This is similar to our smaller triangle, ADE. So in order to solve this, I have to find those corresponding proportional sides. So what side is going to be corresponding to my variable x? 6. So BC is going to correspond to 6. Because ADE is my second triangle, I'm going to put 6 in my numerator and x in my denominator. Now, I have to find another set of proportional sides, another set of corresponding sides. What other information am I giving? 3 and 2. So how can I use that to... What was that? Right, but we don't know any information about those ones, so we can't necessarily use those triangles, or those sides. So that's good, we have those, but not information on them, so that's it. So we'll have to use AD and DB, which is 3 and 2. What was that? Yeah, so we automatically know our triangles are similar, because of those parallel lines. So we don't have to worry about proving that the triangles are similar, but we just want to be able to use those side lines to help us find those proportional.
So could you not do theorem 2?
Can we?
Oh, I just didn't know if there's no one thing.
So let's think, why is this wrong?
Side angle. It's on the overall side.
So in order to do proportional sides, we need to use those full side lengths. So these are 2 full side lengths. 3 is a full side length, but 2 is just a small little piece. What is that full side length? 5. It's going to be all of that side length.
Would you do 5 over 1?
So 3 is still going to stay in my numerator.
Why? 3 is not a big piece either, but it's the second triangle.
But if we look at our 2 triangles, our 2 similar triangles is my blue triangle and my red triangle. So I had a blue triangle divided by a blue triangle side length divided by a red triangle side length. So I'm going to do a blue triangle side length. I need to divide by the red triangle side length, but that red triangle side length is full 5. And so 3 over 5 over here. And from here, we can then go about solving it. Cross multiply, divide. Like, which one comes first or after?
Or like, what if you just like circle 3 first?
No, it's as long as you're multiplying a top and bottom on opposite sides, it's going to work. So that gives me 30 equals 3x, which if I did it the other way, it would be 3x equals 30, which is still the same thing. Divide by 3, divide by 3, and x equals 10. And that would be our length of BC. So we just have to show that if we're looking for one of those bases of our triangles, typically you're actually going to have to use the fact that our triangles are similar and not the fact that the side lengths are proportional. So always be cautious on when you set up those angles, or always be cautious when you set up those equivalent fractions that you're actually using the side lengths of the triangles and not just pieces of the triangles. Other than that, that is where we will have it for today.